Hello, everyone, and welcome to a new program of the BioTech Talks podcast, the podcast about science that wants to bring biomedical engineering to a broader audience. Today, we have a really broad topic in which we will talk about biomechanics and bioelectronics. Focused on bioelectronics, we have with us Miriam Caravaca, who is working on a biosensor which will be integrated in an electronic device.
Thanks, Andrea. And thanks to that, we can design cells to achieve different functions due to this interaction between these electronics and living systems.
Sergi Navarro is testing the use of non-invasive chronic stimulation by means of electric pulses to improve memory persistence in mice.
Yeah, that's right. I think that I'm not doing bioelectronics at all, because for me, this would be like bio-inspired devices. And in this case, I'm doing a neurostimulator for mice in order to do neurostimulation. And in this way, it's clear that there is a coexistence between electronics and biology, but maybe this is not bioelectronics as itself.
And Marcus Tick is working on an implantable nerve stimulator.
The objective of my bachelor thesis is basically that we can give physicians a tool to test in mice how vagus nerve stimulation affects several diseases like obesity or sepsis, and also is a treatment that is already approved by the FDA for depression and epilepsy.
And in the biomechanics field, we have Maria Ballard, who is working in the modeling of bones with finite elements.
My bachelor thesis main goal is to improve a current knee model for evaluating osteoarthritis, and these models that are used right now are not taking, well, obviously the model is composed by different materials, so like the bone, the cartilage, the ligaments, and everything, but they are not taking the bone as a solid with its properties, but as a surface. And even though that might be a good approximation, that is a good approximation and leads to a correct diagnosis and treatment, for a more precise diagnosis, we need to treat the bone as it is, as a solid and with its properties, which are going to be different for a healthy and for an osteoarthritic patient.
And finally, myself, that I'm working in an agent-based model to later on integrate biomechanical data. And in my case, I'm not developing an entire biomechanical work. What I'm doing, in fact, is modeling the cellular interaction of the chondrocytes, which are the cells that we can find in the knee. By the moment, the work is only focused on the molecular pathways that regulate the functionality of the cells, and that's why there's no biomechanics by the moment. But even at a certain moment, independently of the integration in my bachelor thesis or not, the idea is that these molecular pathways that regulate the chondrocytes, if are activated or not, it can be done by mechanical forces that can be extracted from works as the one of Maria, and that can finally modify the results of the network that I'm developing right now. From the application cases that we have for today, we could say that in bioelectronics, we tend to interact with an element by means of an electronic device to obtain results, while in biomechanics, we are more prone to use them to analyze the results and that are given and then extrapolate some conclusions. However, reality is much more diverse, and there are thousands of applications which you may already know that may not match the aims that we are following today. A perfect example for that could be the combination of bioelectronics and biomechanics on a robotic arm prosthesis, which is designed to simulate the functions of an arm. So we need to study their biomechanics, but it also needs to integrate an input signal, either mechanical or electrical, to transform it into an electric pulse that habilitates the movement of the prosthesis. Going back to the idea of bioelectronics and biomechanics is to apply more technical fields to biology, it might be interesting that each of us explain how we build this bridge to communicate the ideas and results from mechanics or electronics and integrate it into a biological and medical field.
We can distinguish two big parts in my bachelor thesis. The first one is the biosensor, and the second one is all the electronics system which is behind. But the second part is takes inspiration from the IGEM 2020 team to build a turbid state in order to have and perform the better conditions for the cell's growth in terms of temperature and agitation of the culture.
Thank you, Miriam. In my bachelor's thesis, it's quite difficult, like, to find this equilibrium between biology and electronics, because I'm working with animals, but in the same time, I'm building this stimulator. So the thing is that you make a design, okay, and you go like, okay, this is going to work, this is amazing, I'm going to try it on animals, and then it's a complete disaster. So it's just a try and failure process, and you just go design something, you produce it, you test it in animals, and then you go like, okay, this is not working, I have to change this and this. And this is just like a wheel, you just keep doing this again and again, and it's kind of a pain in the ass, but it's also like really beautiful in the same time. And the thing is this, that on the one hand,
what I'm doing, it's exactly a bridge between this mechanics and biology, and really what saying Maria. She's working on an organ level, let's say, and my work would be focused on translating this organ level to a tissue level, to translate the mechanical forces to the behavior of the cells. So as I explained before, I am working in a model of the cartilage at the tissular level, and I am expressing the different cells and molecules as different agents that can be activated or inactivated. So once enough mechanical information has been obtained from works as the one of Maria, we hope to be able to relate this mechanical information to different concentrations of the components of the cartilage, as we know that there are some cellular receptors that are able to sense these mechanical stresses. So at the end, what we need is to obtain the mechanical forces from the model and relate them with a given expression level that can be extracted from clinical samples and clinical studies to later on integrate them both in the model, translated into some parameters that define the equations of this model in which I am working. Okay, and finally, let's try to put more examples over the table. And for that, it could be interesting to know which similar works do we know, or in which other works we based our work, as Sergi mentioned, when talking about a previous bachelor thesis.
Yeah, in my case, the hotspots of the project are probably that we aim to do something which is open source, and this is something that at least I have been able to find when it comes to implantable vagus nerve stimulators. This is type of stimulators that you don't have to wire to external current sources or anything, and that in fact is open source, so you don't have to buy any type of license or anything like that, and you can just program the stimulator in the conditions that you want for your stimulation, because there are different types of parameters that may be interesting for one application or for another. For instance, frequency, current, and this is something I haven't been able to find in the state of the art. But there are some examples of implantable stimulators for vagus nerve.
In my case, as Andreu said, obviously because we are in the same team, I am also using like something that the biomechanics and microbiology team here at UPF created, and it's the knee model that I commented before. It's the these osteoarthritic knee model, which are also the current knee models used in all state-of-the-art that I found.
I continue with a project that was in my lab, which is synthetic biology for biomedical applications. So actually, it's not necessary to start from the beginning. You have a base in which you can try and it's that important point that you have a base. You didn't start from zero, so you have something in which you can take part.
Okay, thank you so much for your comments, and I think that this could be everything for today. If you have found our podcast interesting, remember that you can subscribe to our YouTube channel, as we will be posting the BioTech Talks for each of today's guests and many other students. And again, you can also follow us on our social media, and we hope to see you soon. Bye.
See you. Bye.
thank you, Andrea.
Bye.
Bye.